Hello everyone, my name is Jinfeng Wing. I am a PhD student from University of Notre Dame. Today I'm glad to present our paper, Traceability Transformed, Generating More Accurate Link with Pre-trained BERT Models. Software traceability is a technique for tracking the relationships between the software artifacts, such as the requirement, design definition, test case, and source code. With these links, engineers can quickly find answers for the queries such as how is the feature implemented in our code base, whether this new function has been covered with unit test. One application of software traceability in open source project is tracking the issue and the commits. The issue can be either bug report, feature request, pull request act. In project with scope maintenance, project owner will manually annotate the related commits to the issues. In this study, we use the issue commit tracing as an example to demonstrate the effectiveness of the transformer-based models. Given an issue and commit, we will use the issue description, code change set, and the commit message to predict whether they are related or not. The manual annotated links will be leveraged as our training examples. Our approach is based on study of CodeBERT, released by Microsoft. In the pre-training stage, a massive language model for the programming language is pre-trained with the function definitions mined from the GitHub. The language model named as a CodeBERT will be then used to formulate the trace models responsible for the relation classification. Before we directly fine-tune the trace models on the traceability data, we introduce a code search problem as an intermediate training step to provide the fundamental knowledge between the natural language and the programming language. In this step, trace model is trained to predict whether a function specification and the docstring are related or not. At last, we will fine-tune the trace model with the issue commit links mined from the GitHub projects to specialize the trace model with the software traceability. There are many differences between the code search and the traceability. First, we can see in the code search problem, the code has a consistent structure, where in the issue commit traceability, only the diffs between the two versions of the code will be used. Second, the population of training examples in these two problems are dramatically different. Issue commit traceability usually have very limited training set, as it requires the manual annotation. Also, the training examples in the software traceability are more noisy than the code search, because the maintainers may miss or make wrong links during the manual processing. This will rarely happen in the code search problem, because the docstring and the function specifications are in a one-to-one relationship. From this perspective, traceability is a more challenging problem than the code search. However, both tasks train models to discover the relation among the natural language and the programming language tokens. For this reason, traceability can transfer knowledge from code search problems as an actual training objective. In this study, we also introduced 3 different types of architectures for the trace models. Depending on the usage of the BERT model within the architectures, we name this as the Siamese, single, and the twin architecture. In the Siamese architecture, we use a shared BERT model to encode both the issue and the commit. It will produce 2 separate semantic representations for the artifacts. We then merge these 2 hidden states to create the feature vector for the given artifact pair. At the top, a neural network will predict whether these 2 artifacts are related or not. In single architecture, we concatenate the issue and the commit as a single sequence, separated by the special token. Then the BERT model will produce a single semantic representation for this artifact pair. The neural network at the top will then use this fused feature vector to produce the prediction. The twin architecture have a very similar mechanism as the Siamese. However, it uses 2 different BERT models to encode the natural language and the programming languages separately. Intuitively, the single architecture can produce prediction with better accuracy, because it allows the language model directly to learn the relationships at the encoding stage. The Siamese and the twin models lack such information and primarily rely on the neural network to identify the artifact relationships. However, one benefit of the Siamese and the twin model is that they decouple the encoding of the artifact pair. For example, given a trace problem with n multiply n candidate links, they only need to encode the two n artifacts for one time, and then reuse the encoded hidden states to formulate the candidate links. In contrast, the single model needs to encode all of the n multiply n candidates, which will significantly increase the prediction time. In this table, we show the effectiveness of our models on the code search problem. The result will start are models trained with the negative sampling techniques, where the first 4 rows are the same models without the negative sampling. We can see the negative sampling is beneficial for the model training. The results show that all the 3 types of the trace model significantly outperform the conventional IR trace models. It also beats the RNN-based trace models using the long short-term memory and the bidirectional GRU. The results reported from other studies are shown in the last 3 rows. The MSC referred to the results reported by the Microsoft, which used a similar architecture as a single model in our experiment. The closed MRR score indicated we replicate their results properly. Then we apply our model on the issue commit tracing problem. We experimented the models on 3 open source projects, including the PGCLI, Flex, and the Cursor. The model with T means that the model has been applied to resolve the code search problem first, before fine-tuning on the tracing problem. Our results show that leveraging the code search as an intermediate training step, we can stably improve the tracing performance on the issue commit challenge. Either with or without the intermediate step, our approach clearly outperforms the conventional IR-based trace models, including the VSM, LDA, and LSI. The RNN-based trace models, which was developed for the natural language tracing, failed in the issue to commit tracing problems. The model either underfit or overfit the dataset due to the size of the training examples. This result indicates that our approach can significantly reduce the number of training data compared to the conventional deep learning-based methods, such as thus it has a broader application in practice. We also record the train and prediction time of the 3 models on the PGCLI dataset. As we can see, the prediction speed of the Siamese and the twin model is much faster than the single models, and at the meantime, the Siamese architecture maintains relative close performance to the single model. For conclusion, in this study, we propose a solution for resolving the traceability challenge using natural language and programming language artifacts by taking the issue and the commit tracing as an example. We propose 3 language models-based architecture, in which we find the single architecture achieved the best performance, where the Siamese achieved the close performance with a higher speed. We introduce a framework with 3 main steps of training. In this framework, a language model for the programming language is firstly pre-trained from the function specifications, and then a code search problem is introduced at the intermediate training step. At last, the model is fine-tuned on the issue commit links to specialize the software traceability. Based on our observations, the intermediate training can stably improve the performance of issue commit tracing. And most importantly, we find our approach can outperform all the conventional IR trace models and adapt to the scenarios where RNN-based trace models cannot handle. The high accuracy for the approach on real-world open source project indicate that the application of our methods in practice. So thank you for listening, and thank you for your time in listening.
Yes, so welcome to the Q&A of the second paper of the session, Traceability Transformed, Generating More Accurate Links with Pre-trained BERT Models. Junfeng is here to answer your questions, and congratulations again for the ACM 6 of Distinguished Paper Award.
Thank you. So let me read the question.
Yeah.
I have one clarification question. The pre-trained BERT model encoders were not modified when training on the trace link data, right? No, like actually the BERT model is like part of the whole classification models. So when we like doing the trainings, actually it will change the parameters within the bottom BERT model as well. So like during the trainings, when the training data come in, it will modify the parameter, both the top classifier and the underlying BERT models. So does this answer your question?
So it modifies.
Yeah, it modifies both the classifier on the top and the BERT model itself. Yeah.
Yes. Okay. I guess that's normally how BERT models are used, right?
Yes, this
they
is
have
very
pre-trained. Yeah.
Yeah. So this step is actually called fine-tuning, like using the project-specific data to change the parameter within the language models to let it specialize for the task you want.
Okay, thank you. Any other questions? While waiting for the questions, I can ask something. You mentioned something about, let me check first. Regarding the training data, the size of the training data, you said other models like RNN didn't work. But I thought BERT models also require quite a lot of data instances in training. So
right.
How did you solve that? Why do you think the size of the training data affected other models but not yours?
Oh yeah. So I think we add like an intermediate training step. Like this is the most important part in the problem we try to address. So like one problems impacting the deep learning methods in the traceability is that the projects actually have very small set of the links. So if you check our data set we use, actually it only have like a few hundreds of links for the training's purpose. And usually this is not enough for deep learning models. So what we leverage is that we use a adjacent problem, which we call like the code search. So it has very high similarity with traceabilities, and it have like a very clean and rich data set. So we actually use the training on the code search problems at the intermediate step, and let the model transfer knowledge learned from learning the relationship between the large code in the code search and the natural languages. By this way, we allow the model to learn, okay, I know this natural language may be related with this ones. And we use like our small data set on the traceability to fine tune like this data to define like, okay, the relevance between the natural language and the code in our scope is in this way. You should learn this ways. So by this way, we can significantly reduce the data we need for training the BERT models.
Yeah, very smart. Okay, another question from Grace Lewis. What do you believe is the main reason for your very good evaluation results? Like outperforming conventional IR trace models requires less training. Partially we answered that, I think, but you can maybe elaborate more on this.
Yeah, so I think the main reasons for outperforming the RM models, because like we introduce like actual data actually as our intermediate step, and we have the large data set, which is the main force of the deep learning ones, which can like exploit the statistics within the large data set. So I think this is the main reason why our result is like way more better than directly training the RM models on the traceability data set itself. And also another reason that like the result is very good is because like how we process the data. So we remove the noise in the data set and make the tracing problem into a very small scale. So this is a very important technique we need to consider when we actually apply the traceabilities. Because like if you like doing a trace on the whole data set, you will involve a lot of noise and you will have like a huge search space. And in most circumstances, you need to do some like heuristic-based approach to reduce the noise. Like you can eliminate the candidate links, which like is absolutely no reason to be connect together. For example, like if a commit is like made before an issue is created, a long time ago, then like they are not likely to address the issues, because like solution cannot appear before the question comes. So like by using these heuristics, you can reduce the size of the question, and this can help you to improve the accuracy a lot.
Okay, one more question. Your dataset contains one-to-one mapped artifacts. However, the real data usually is more sparse. Some artifacts may not be linked to any other artifact. Have you evaluated your model on such datasets?
Oh, so actually, like this dataset, we do not like intentionally make this like one-to-one, but like just like in this dataset, like most issues will connect to just one or two commits. So this is like one behavior we observe in our dataset. Like we do not like manufacturing the data into this format. But like in the code search problem, this is definitely one-to-one. But like in the traceabilities, this is like one-to-many questions we address.
Okay, but normally in your technique, what you require as data, as far as I understand, is you give a source code and an issue and say these are related. And then
Yes.
do you also have negative instances, like a source code and an issue saying these are unrelated? So
yeah, so basically like we formulate this as classification questions. So actually it do not care like whether it's one-to-one or it's one-to-many. Like it can handle like both situations. So like when the model, like from the model perspective, like the candidate come in as one pair. Like the left side is the natural language, the right side is the code, and then it just like predicts score, like how likely they will be related. So like you can like have like a one-to-many relationship in your data set, and the model will process them one by one. And if like you think two of them are true, it will like just okay, these two have like 90% of chance to be true.
Yeah. Okay.
Yeah.
And while waiting for other questions, maybe I can also ask one more. So in the natural language processing area, you know, with BERT models, there's also this new, relatively new concept called fast text. Maybe you heard, which runs a lot more faster, more robust, they say, and works quite well in document classifications. Have you looked at those newest technologies, or?
So I think like when last time I checked the fast text, they're actually like creating the word embeddings for the concepts. And I think there are different technology with the BERT model-based ones. Like they are using different models to create the word embeddings instead of like processing the context, like directly encoding the whole sentences or code. So maybe there is more chance to like apply the fast text into the in the code areas, but I think like they need a different data set to train a dedicated model for the code itself, rather than using the general language models for the code processing.
Okay. One more question, two more questions. Your positive pairs should be minority, right? Much fewer than the negative. Did you balance those during training?
Yes, it's true. Like our positive examples is way more smaller than the negative ones. It only have like less than 1% of the data set. So what we do, like when we do the trainings, we must create a balanced data set.
Yeah,
so
we have 15 seconds, by the way.
Okay, yeah, so we create like a balanced data set for the training purpose, but like when we do the test, it's like unbalanced real data set. So like we're trying to find,
So two more questions you have, but maybe in the discussion.